Before we look further at how to quantify stability using our Bode plots, I want to take a short detour and talk about the Nyquist stability criterion, because this is also a common method used to determine stability of a system. So there's actually two things that we can get from our Nyquist stability criterion. We can determine if our system is stable. So if system is stable, but we can also determine the degree of stability. So the degree of our system stability. And so we're not going to go over how to find the degree of stability, but we are going to look at how we can tell just looking at a Nyquist plot whether a system is stable or not. We're not going to go into a lot of the details of how to construct a Nyquist plot, but oftentimes you can use software packages such as MATLAB in order to create these plots. So let's consider our three-pole amplifier. So our three-pole amplifier that we just looked at, which we said can represent our op-amp circuit. And so we said that we had the loop gain function from before. Well, actually we had our open loop gain, but we can pretty easily convert that to our loop gain if we just multiply by that beta. So we can say the magnitude then is going to be beta times A naught, and that's our low frequency gain. And then from our three pole terms, we get the magnitude by doing square root of A squared plus B squared. So we have square root of 1 plus omega divided by omega 1 squared, square root of 1 plus omega divided by omega 2 squared, and finally square root of 1 plus omega divided by omega 3 squared. So we get something like this for our magnitude. And then we could also show that our phase is equal to negative, and then the quantity, our inverse tangent of omega divided by omega 1, plus inverse tangent of omega divided by omega 2, plus inverse tangent of omega divided by omega 3. So what we want to do to create our Nyquist plot is we want to plot these on our complex plane. So plot on our complex plane to create our Nyquist plot. And so we're just going to go over sort of the basic structure of this, but again, if you're wanting to plot a more accurate Nyquist plot, you're going to want to do that in some type of software package typically. So let's draw our complex plane here. So our complex plane, we're going to have our imaginary axis and our real axis. And so we can see then that our Nyquist plot is essentially going to be a polar plot, where again we're considering our magnitude and phase. So let's sort of think through what's happening as we increase our frequency from 0. So if we think about our magnitude first, we see that for 0 frequency, so if we have a 0 for each of these frequencies here, we're going to have just a 1 in the denominator, and our magnitude is going to be beta times A naught. Similarly, if we looked at our phase information and considered putting in a 0 for each of these frequencies, what we would see is that our angle is just 0. So what that means is if we come out here on our plot, we're on the real axis, and the value of this is going to be our low frequency gain, beta A naught. And so from here, it can be a little more difficult to sort of visualize what happens as our frequency is increasing. But if we think about the Bode plots from the previous video, we know that once we hit our corner frequency omega 1, our magnitude is going to be decreasing, and it's going to continue decreasing as we get to higher and higher frequencies at a faster rate. In terms of our phase, what we saw for our phase part of our Bode plot was that it drops down 90 degrees for each of our poles. So since we have 3 poles, although it's starting at a phase angle of 0, it's going to be decreasing to 90 degrees for our first pole, to negative 180 for our second pole, and then finally to negative 270 for our third pole. So let's kind of put all of that together as we make this Nyquist plot. So what we have is we said our magnitude is going to be decreasing, so we're going to be getting kind of closer to the origin as our phase angle is increasing sort of in or not increasing, it's decreasing. So for instance here, this would be the contribution from our first pole. Our angle as measured from this axis, remember, is our phase angle. So that would be for our first pole. We can keep on going. Now we're at negative 180 and our magnitude is still decreasing. And then finally, we get a phase angle of negative 270. So here would be where we start with our omega equals 0. And over here, we would have our omega equals positive infinity. So at infinity, we see our magnitude has gotten really, really small, infinitesimally small, all the way to 0. And our phase angle is 270 degrees. So along this path, we have, change colors here. Along this path, we have our omega going to infinity. So we could also talk about negative frequencies, although they don't have a physical meaning. They're also usually included in our Nyquist plots. And so what we would see is it's actually just the complex conjugate. So let me attempt to draw this well, but basically it's just a mirrored version of this plot that we have. So I've done a pretty poor job, but basically it should be this blue curve just mirrored up. And so here we're starting at a value of omega equals negative infinity, and we're going up to a value of omega equals 0 right below 0. This would be positive. So here our omega is moving towards 0. Okay. Again, don't worry too much about the negative frequency. So the question then becomes, how do we use this Nyquist plot in order to determine our system stability? Well, let's go ahead and write what that sort of criterion is. So what our criterion is that if our Nyquist plot encircles or even touches or goes through our point negative 1, 0, then our system is going to be unstable. So this is sort of the key thing to using our Nyquist criterion. And so what that looks like up here, so for instance, let's say this was our point negative 1, 0. So in this case, the system would be stable because this curve, this blue curve, is not encircling that, it's not going through that. We could consider a couple different options, so let me sort of erase this real quick. And let's say if the scale of this has changed, so maybe it's expanded, it's gone a little further left. So now maybe we have our point negative 1, 0 here. So in this case, of course, the plot is going through the point negative 1, 0, so this would be unstable. So of course, the last possibility, let me erase this, is if our plot encircles it. Let's see if I can just get that dot. There we go. So if our plot encircles it, so maybe this is our point. Let's get a different color. So maybe this is our point here, negative 1, 0. Then this is also going to be unstable. And so again, if you have access to a software package and you can plot these easily, this is a good way to determine stability. What we're going to look at is an example in our next video, and then after that we're going to see how we can use those Bode plots in order to determine stability of a system and also quantify the stability of the system.